Good day, everybody. Previously, we have talked about in great detail how to draw the Lewis structure of covalent compounds. And today, we are going to talk about how to use the Lewis structure to predict the shapes of the molecules. And this is based on so-called valence shell electron pair repulsion theory, or VSEPR theory, VSEPR theory. This theory is based on the idea that negative charges of electron groups will repel each other. The electron groups is either a lone pair or it could be a chemical bond, a single bond, double bond, or triple bond. To remember, no matter if it's a single bond, a double bond, or triple bond, they are all considered as one electron groups. A triple bond is not 3 electron groups. It's one group of electrons. That's why it's considered as one electron group. For example, let's look at this structure. Here's the Lewis structure we arrived at last time. With this Lewis structure, we only look at the center atom. So that's the center atom. On the center atom, we have one lone pair. That's the one lone pair. And we have 3 bonds. This is one single bond, and one double bond. Each bond, no matter if it's single, double, or triple, they are all considered as one. So we have 3 bonds. Put this together. So we have a total 4 electron groups. And this is called the steric number. So steric number is 4 because it has 4 electron groups. Give you another example. For carbon dioxide, carbon is surrounded with 2 oxygen atoms with double bonds. So for carbon center, remember the shape is all about the center atom. There is 0 lone pair. 0 lone pair. But you do have one bond. So it's a total of 2 bonds. So for this reason, steric number is 2. Let's do another example. This is the Lewis structure of water. On the center atom, oxygen, we have 2 lone pairs. And we have one bond. So it's 2 total bonds as well. So for this reason, the steric number is 4. Excuse me. Right. So how can we use the steric number to predict the shapes of molecules? Let's start with the special type of shape, which is called the shapes of electron groups, or electron group geometry. There are only 5 basic electron groups. For example, if steric number is 2, we have 2 electron groups represented by the 2 lines over here. Okay. So if we draw it, we can use a dot to represent an atom. And on either side, you have an electron group. So the bond angle is 180 degrees. Similarly, if you have 3 electron groups, we can draw it from top down. When you look at here from top down, okay, it looks like this. So that's the center atom. Center atom is connected with 3 electron groups, okay, using 3 sticks to represent it. And the bond angle is 120 degrees. For tetrahedral shape, Okay, as you can see over here, that's a tetrahedral shape. Basically, if you draw it without the sphere, you can draw a center atom first. Then the solid line represents this electron group is in the plane of that paper. And then we use the wedge to indicate that this electron group is sticking out of paper toward us. And for the hashed line, that means this electron group is actually sticking to the back of the plane of paper. So this is tetrahedral shape. And the bound angle is 109.5 degrees C. When steric number is 5 or 6, we have trigonal bipyramidal shape and octahedral shape, respectively. But for introductory chemistry, we'll be focused on the first 3 electron geometries only. When you have the correct electron geometries, you'll be ready to derive the corresponding molecular geometry. Do remember, when Sn is 2, we have a linear electron geometry. When Sn is 3, we have a trigonal planar electron geometry. When we have Sn is 4, we have a tetrahedral electron geometry. It could be represented in this way. So let's see how electron group geometry or electron geometry is related to the molecular geometry. In the molecular geometry, molecular geometry is the electron group geometry with the lone pair electrons disregarded. Okay, so molecular geometry is the electron geometry with the lone pair electrons disregarded. For example, when we look at the 2 electron groups, we have carbon dioxide. In this case, the electron geometry, for sure, it's 2 electron groups, so that's linear shape. Okay, usually, at least you will have 2 groups surrounding the center atom. So in this case, there will be the molecular geometry will be exactly the same. It will be the same, and the bound angle is 180 degrees. So this is also linear. When we look at BF3, boron is connected to 3 fluorine atoms by a single bond. In this case, we have at the center atom, this center atom, it's 3 electron groups. Okay, 3 electron groups. So Sn number is 3. So the electron geometry over here is the same as the molecular geometry because there is no lone pair. So this is called a trigonal planar. Okay. And the bound angle is 120 degree. So molecular geometry is exactly the same because there is no lone pair electrons on the center boron atom. This is also called a trigonal planar. Let's look at another shape. For example, the sulfur dioxide. When you do the Lewis structure correctly, you would arrive at the structure that looks like this. Sulfur is connected to a single bond on one side and a double bond on the other side, with the lone pair sitting at the center as well. So over here for the sulfur center, we have one bond, two bond, so two bonds, and the one lone pair. So that's 3 electron groups. Sn is also 3. So for the electron geometry, the electron geometry only depends on the total number of electrons. Okay, excuse me, this is 3 electron groups. Okay, so total number of electron groups is 3, so it will be exactly the same in the electron group shape, or electron shape, simply put. Okay. However, for the molecular geometry, we have a lone pair here. So when we draw the Lewis structure to begin with, we draw the 3 electron groups, but the group that has a lone pair, we're going to use a rabbit ear to represent it. So when you look at this structure, okay, look at the molecular structure, this portion with the lone pair is disregarded, but it's still there. Remember, this portion is disregarded, but it is still there because it determines the bond angle. So the bond angle over here is still about 120 degree, not exactly 120, but it's about 120. However, when you talk about the shape of the molecule, this portion is disregarded. This portion is disregarded. We only consider this atom, that atom, and this atom. The lone pair is disregarded. Here, this portion is disregarded. So with this only, the atoms only, without considering the lone pair, so here we have something like this. So that's the same as this. So this is about 120 degree. So we call this bent, or sometimes we can call this angular, which is exactly the same. What about 4 electron groups? Steric number 4. For 4 electron groups, for example, CH4, methane, we draw the correct Lewis structure for CH4 or methane molecule. Okay. For carbon center, we have 4 single bonds and no lone pairs. So steric number is 4. Remember, for steric number 4, all steric number 4 will give you 4 electron groups, which means it will be tetrahedral. The wedge used to represent the electron group that is sticking out toward us, and the hashtag. And the hashed line is actually sticking backward. Okay, so there is no lone pair here. This bond angle is 109.5 degree, and this is called a tetrahedral shape for the electron geometry. For the molecular geometry, it's exactly the same because there is no lone pair present in this structure. Bond angle, the same, 109.5 degree. It's tetrahedral. What if you have one lone pair for steric number 4? For example, NH3, ammonia. So when you draw the correct Lewis structure, so when you look at the drawing on center atom, you have one lone pair, and you have 3 single bonds. That's 3 bonds. So 1 plus 3, that gives you Sn being 4. So electron group shape still the same, which is tetrahedral. The bond angle is 109.5 for all tetrahedral shapes. However, for molecular geometry, we're going to draw the electron geometry first. But then, for the lone pair electrons, we use a rabbit ear to represent it. Okay. To remember, for the molecular geometry, we disregard the lone pair portion, or this portion is disregarded. So this whole structure is the equivalent as this. Okay. And we give this a name, so you can actually draw the bottom. This makes a triangle out of it. Okay, so this name, this shape, we call this trigonal pyramidal. What about water? For water, when you draw the Lewis structure, in this Lewis structure, as you noticed, there's two lone pairs over here and the two single bonds. So Sn is 4. Right? They all share the same tetrahedral electron geometry, so it's also tetrahedral. However, when you look at the molecular geometry, there are two lone pairs over here. So we use a rabbit ear to represent the lone pairs. To remember, for molecular geometry, we disregard the lone pairs. So for this reason, this for molecular geometry, it's the same as this. The bond angle is 109.5 degree. And this shape is called a bent shape. Right. So notice that for all electron group shapes, as long as the steric number is the same, right? Steric number is the same. For example, Sn is 2. You always have electron group as the linear. Electron group Sn is 3. It's always trigonoplanar. Trigonoplanar. For Sn is 4. It's always tetrahedral. 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 There's no exception. However, for the molecular geometry, depending on the number of lone pairs, here in this case, there is no lone pair. So the molecular geometry is the same as the electron geometry. However, if you have lone pairs, as you see in this sulfur dioxide example, then the molecular geometry and electron geometry is different. Okay, similar. No lone pair, the same electron geometry and molecular geometry. However, if you have lone pair, the electron geometry and molecular geometry, they are different. Alright, hopefully by now you have mastered how to get the correct electron geometry. Then you disregard the lone pair and you get the molecular geometry. The electron and molecular geometries of several examples are summarized in this table. You can have a look at it. With this information and knowledge, we are able to explain why oil and water don't mix. The reason is because of the polarity of the molecules. Okay, because oil is nonpolar and water is polar. Polar stuff will not mix with the nonpolar stuff. But how do we know water is polar and oil, or mostly hydrocarbons containing hydrogen and carbons, why are they nonpolar? The polarity is related to the electronegativity. Look at the Lewis structure for water, H2O. The two bonds between oxygen and hydrogen consist of, you have a single bond and over here, right? And you also have two lone pairs over here, right? The oxygen and hydrogen atoms each donate one electron to this electron pair. However, they don't share them equally. So these electrons inside the single bond, you have two electrons. Inside that single bond, you have two electrons as well. However, the two electrons inside this bond and that bond, it's not shared equally between oxygen and hydrogen. The oxygen atom takes more than its fair share of electron pair. And this ability of an element to attract electrons within a covalent bond is so-called electronegativity. And oxygen is more electronegative than hydrogen, which means that on average, the shared electrons are more likely to be found near the oxygen atom than near the hydrogen atom. Consider the representation of the OH bond. The oxygen atom is getting larger share, and this will have a partial negative charge because the electrons are negative charged and it's not evenly shared between oxygen and hydrogen, because oxygen is more electronegative. More electrons are sitting on oxygen than on hydrogen. So that's why this end, oxygen end, is partially negative charge. We use delta minus to represent it. And the hydrogen atom is getting smaller share of the shared electrons, so it's partially positively charged. So we use delta plus to represent it. The result of this uneven electron sharing is a dipole moment, which is the same as a separation of charge within the bond. Then what is a polar bond? What is non-polar bond? So when you have the molecule, when the covalent bond has a dipole moment, or if the electrons between two atoms are not evenly shared when they form a covalent bond, then this bond is called a polar covalent bond. The magnitude of that separation of charge, or the magnitude of a dipole moment, and the polarity of the bond depends on the electronegativity difference. So electronegativity, we use En to represent. The difference, delta En, will decide the bond polarity. The larger the difference of electronegativity between the two atoms, then the more polar the bond is, because it will have greater dipole moment. The bond is more polar for this reason. The value of the electronegativity is assigned using the relative scale with which fluorine, the most electronegative element, has an electronegativity assigned to be 4.0. And the Linus Pauling was the person who introduced the electronegativity scale used here in the next page. He arbitrarily set the electronegativity of fluorine at 4.0 and computed all other values relative to fluorine. As you can see in this periodic table, for main group elements only, fluorine has the largest electronegativity. This end has the largest electronegativity, top right corner, and left bottom corner has the smallest electronegativity. What if two atoms have exactly the same electronegativity? For example, in chlorine, which is a diatomic element, it forms a single bond between the two chlorine atoms. The electrons, that's the two electrons that are used to form this single bond, is equally shared between these two chlorine atoms because they are exactly the same. In this case, we call this bond pure covalent bond. And because the electrons are equally shared, there is no dipole moment, and this molecule is said to be nonpolar. If there is large electronegativity difference between the two atoms in the bond, such as what occurs between the metal and the nonmetal, then the electron is completely transferred and the bond is ionic. For example, you have an NaF. The electron negativity difference between these two atoms are really big. Similarly, in table salt, sodium chloride NaCl, sodium completely transferred in the electron to chlorine. They are not even shared in this case. So we call this type of bond ionic bond. If there is an intermediate electronegativity difference between the two atoms, such as between two different nonmetals, then the bond is polar covalent. For example, HCl bond, HF bond, okay, HBr bond, CO double bond, etc. When the electrons are unequally shared, the end that is more electronegative, we use delta minus to represent the partial negative charge, and delta plus to represent partial positive charge. Usually, when the electronegativity difference is between 0 to 0.4, we say the bond is pure covalent, or we call that nonpolar bond. If the electronegativity difference, delta En, is between 0.4 and 2, then it forms a polar bond. If the difference is greater than 2, it forms an ionic bond. When polar bonds are formed, and if the polarity of each bond is not totally cancelled out, then we have a polar molecule. So basically, a polar molecule is one with polar bonds, that's the precondition, with polar bonds that add together and they do not totally cancel out each other. So you will form a net dipole moment. For example, when you look at CO2, this molecule, for each CO bond, because carbon and oxygen have different electronegativities, so there is a big difference between electronegativity, which means CO double bond is very polar. And the other CO double bond on the left side is also very polar. However, the polarity, when you write the polarity, I'm going to use an arrow with the plus sign on one end to represent the left side bond polarity. And for the right side, let me erase this one. And for the right side, we use the same, an arrow represent the direction of the bond polarity, and the plus sign on one end means that's the partial positive charge end. Although both CO double bonds are polar, however, the polarity cancels out because we have 180-degree bond angle over here. So the tug of war is balanced. So in this molecule, carbon dioxide, we have polar bonds, or more specifically, it's CO bonds. However, the molecule is non-polar because the bond polarities is totally cancelled out. Let's consider the situation for water. In water, you also see two polar bonds, as you see over here, because oxygen is more electronegative than hydrogen. So the bond polarity is actually pointing toward oxygen. Oxygen is partially negatively charged. When you look at this case, the two polarities and these two polarities, they do not totally, two bond polarities do not totally cancel out. Okay, so basically it's like they are pushing oxygen up. Okay, so for this reason, this molecule, water, is polar because the bond polarity of the two OH bonds do not totally cancel out. So this is a polar bonds. We do have polar bonds here. We have OH bonds, and the molecule in this case, it's also polar. It's a polar molecule. For the more complicated situation, for example, in BA3, you have 3 BF bonds pulling in 3 symmetrical directions. So the bond polarity is totally cancelled out. The tug of war is totally balanced. So this molecule, BF3, is actually nonpolar. This molecule is nonpolar. But do remember, as we analyzed, each bond is a polar bond. Okay, let's look at another example. What about NH3? So when you look at NH3, look at NH3. So we write the electron geometry, and then we use the Rabier type of lobe to represent the lone pair. When you consider the bonds, that's the nitrogen here, nitrogen, that's hydrogen, hydrogen, and hydrogen. We have 3 bonds. This bond is pointing toward nitrogen, this bond pointing toward nitrogen, and this bond pointing toward nitrogen. Okay, if it's NH4, if there is no lone pair, all bond polarities will be cancelled out. The tug of war will be balanced. However, in this case, this position is not an NH bond. It's replaced with a lone pair. For this reason, NH3 is a polar molecule, because the tug of war is not balanced. Right? If in the tetrahedral shape, for example, you have carbon tetrachloride CCl4, the Lewis structure is listed over here. Remember, when you draw the Lewis structure itself does not represent the real situation. It does not represent how the molecule appear in the 3D space. You have to get the correct electron geometry and then indicate the possible lone pairs and figure out the molecular geometry and see if there is a polar bond. If there is polar bonds, you will need to see if the polar bonds have the polarities cancelled out. If yes, it will be giving you a nonpolar molecule, or else it will be a polar molecule. So in this case, carbon center has 4 single bonds with no lone pairs. So electron group shape will be, so here's the electron group shape for carbon tetrachloride. It will be carbon over the top. It will be Cl. I'm not writing the dots yet. So this wedge means it's sticking out, and then the hash line means it's sticking back. So you look at that, each carbon chlorine bond, Cl bond, is polar, and it's pointing toward the chlorine for each bond polarity. However, because carbon tetrachloride is in the ideal situation tetrahedral shape, the bond polarity are totally symmetrical in all directions, so the tug of war is totally balanced. So this molecule does have polar bonds, however the bond polarities totally cancel out. So it's polar bond, however it's non-polar molecule. So, alright, that's it for today, and hopefully you can get more exercise, and see you next time. Have a good day. Bye.